It's on now? Okay. Yeah, but okay, can you? I need to hold it. Okay. Ah, okay.
Okay, so it's a really great pleasure to welcome Massimiliano Esposito to give this fifth set of lectures in this school. So Massimiliano is a professor of theoretical physics in University of Luxembourg. So he'll lecture on stochastic thermodynamics of macroscopic systems.
Thank you very much. It's a pleasure to be here. Thank you for the invitation. So yeah, the lecture will be about stochastic thermodynamics. So who hasn't never heard about stochastic thermodynamics? How many of you have heard about stochastic thermodynamics? Okay. So of course it has to do with thermodynamics and with stochastic processes, and it has to do with how to connect energetics, because thermodynamics concerns the energetics of a system, with its dynamics, and the dynamics will be typically stochastic because we will be concerned with open systems, so systems that are interacting with the surrounding. And it's this interaction with the surroundings that will provide stochasticity to the system. So we will go in detail through the setup. I think, I will see how fast I proceed. So the plan is not yet fully settled. But the first part will really be the basics, basic formalism, with some emphasis on the role of conservation laws, because this plays an important role. And I think this is an aspect that is less covered in textbooks. By now, there are 2 textbooks on stochastic thermodynamics that you can find. There are also very good reviews on the topic. But my focus will be conservation laws, the role of conservation laws, and the second one is going towards the macroscopic limit. And I will try to give you kind of a pictorial idea of why I think this is an interesting and new development to connect back to the macroscopic world, and just 3 which might mix with 1 and 2 is some applications. And I think I mentioned to Abhishek, I will try to do everything I can on the blackboard, but I know already that I'm going to be too slow on the blackboard. So towards the end, things that I didn't cover but I really want to cover, I might go to slides on the last lecture to give you to kind of get to the end of what I didn't manage to cover on the blackboard. But I think it's good to start on the blackboard so that we understand the basics, and then it's going to be also easier for you if you want to understand better what I show on the slides. You'll have the basis there. So slides on things I could not cover in 1 and 2. And going back to this pictorial representation, this is kind of my way of historically rationalizing things. Imagine that this is the distance from equilibrium. Distance from equilibrium. And that this region is equilibrium. This is close to equilibrium. And here we are far. And this is the axis of the size. So this is like the micro world and the macro world. The trend of thermodynamics, you know, I mean, thermodynamics is traditional thermodynamics is equilibrium thermodynamics, is a science for macroscopic systems at equilibrium. Okay, that's what is taught in first or second year university. And it's a science that was developed with the Industrial Revolution, played a key role across almost every science. Yes? Okay, I will try. If I don't, remind me. Yeah, so this is macro. And the pioneers, Boltzmann, Maxwell, gave rise to this science that is statistical physics. And statistical physics initially was also for system at equilibrium, although the Boltzmann equation is already out of equilibrium. But let's say the body of knowledge that we now study as equilibrium statistical mechanics was explaining these macroscopic laws in terms of statistical properties describing microscopic degrees of freedom, probabilities describing microscopic degrees of freedom. Then, this is beginning of the 20th century, there was this field called linear irreversible thermodynamics, which was basically assuming that locally things are at equilibrium and that the system is not too far from equilibrium, how to extend thermodynamics to the non-equilibrium regime, but still close to equilibrium. And the statistical underpinnings of that theory were developed, I think, in the 50s, 60s, with Kubo, Green, so linear response theories. And you see, I find it interesting that we always kind of got into this direction. And funnily enough, this, what is now called stochastic thermodynamics, is a way to build, I mean, historically, you can say that it started around the late 90s with Jarzynski, Leibowitz. These are all papers, Crookes, from Kurchan. It's hard to do the history because it's complicated, but it's late 90s, but of course you can find precursors of that in the 70s, 80s, Schnackenberg, even Leibowitz to a certain extent. Then the Brussels School. But let's say 90s, and the field really matured in 2010, I would say. People understood how to really deal with describing the thermodynamics of small fluctuating systems. And this is what I'm going to give in this part here. So this is the typical stochastic thermodynamics, describing small fluctuating system, quantum dot, single molecules, colloidal particles, and doing the energetics of those systems. And then the question, which was also kind of a debate in the literature, was, okay, but what does this has to do with what we know from traditional equilibrium thermodynamics? And this is what I'm going to kind of answer here. I will not have time to cover everything, as I said, but it's taking systems which have a macroscopic limit and take the macroscopic limit of this theory to go to a non-equilibrium thermodynamics that really comes from this underlying stochastic description. And in between, but this I fear I will not have time to cover, there's using large deviation theory. One can also study macroscopic fluctuations. So at this level, the theory is deterministic. At this level, it is fully stochastic. And as we take the macroscopic limit using tools of large deviation theories, telling us how probability concentrate about their most likely behavior, one can use large deviation theory to characterize the large fluctuation around these deterministic behaviors. So the full, I need to use this tool now. It's new for me, but so the full theory is now summarized in something that will most likely be published in Review of Modern Physics. We are resubmitting now, but it's already on the archive. It's with my postdoc, my former postdoc, Gianmaria Falasco, and myself. And you can find it on archive. It's 2307-12406. And it's called precisely microscopic stochastic thermodynamics. And since I'm now giving references, let me just point out that the basic formalism I'm going to give here is mostly inspired by my former PhD student Ricardo Rao and myself. This was a New Journal of Physics paper, volume 20. 023007 in 2018. Okay. So let's start. I think the first two lectures will probably be on the basic formalism, and then we will move to the macro limit. And in between, I will try to give you various applications. Okay? Good. So part one. I will really start by emphasizing the mathematical aspects of the theory. So let's first start with the dynamics, stochastic dynamics. So what we are dealing with here is a network of states. So we have some states that are denoted by nodes. And we have transitions between states. And the probability per unit time to observe a transition, I use the matrix notation from J to I. So J to I. This would be this. Allows us to write a Markov jump process describing the probability to be on a certain state I. And the time derivative of that probability is given by summing the probability to be on every state times the probability to jump from a state J to a state I. I included here, I could rewrite this as J different from I, W, I, J, P, J, and then I would have, I left out this diagonal term here, and the diagonal term by construction is minus the sum of the non-diagonal one. So this guy is minus the sum over I different than J. Yeah. And this is a convention. So in other words, it means that when I write a rate matrix, I know that when I sum every element of a column, the diagonal one is minus the sum of the non-diagonal ones, okay? So every element on the diagonal, which is this WII, is the sum, is minus the sum of the other one. So if we take an example, W11, W21, W31, and we keep filling the matrix, this W11 is equal to minus W21 minus W31. Yeah, well, this is this was my next step. This is why I wrote this, because you can basically write this now as j different from I, Wij Pj minus Wji Pi. And now you have the interpretation that you want. You see, the probability to jump from another state into state I minus the probability to jump from state I to another state j. And this is where you have. And most of the time I will stop using, when I write it like that, I don't need to say different from I, just because if I include I and II, it drops from both sides. Okay? What is the question? It's just because this is this. So this is, I'm just, okay. What else? Yes, for obvious probability conservation reason, and this follows from, I should have actually mentioned this, that this is a consequence of probability conservation, because if you sum this over I, you want that this is 0, right? Because probability needs to be conserved. And so the property that the sum over I of Wij is equal to 0 is a necessity of preserving probability. And this is what leads to this. Okay, now let me also introduce a notation that will be convenient for later. Is the notation in terms of edges, because now I use the notation only in terms of transition between I and j. But what I want to state now is that I may have different types of transition between pairs of states. Okay, so I may have this one, but also this one. From the dynamics point of view, it doesn't matter, because I only care about the probability to be on a state. But because I'm going to care about exchange, what causes this transition and what is exchanged with the reservoirs later on, I may want to account for the fact that there might be different mechanisms for doing a transition. Let's say a physics motivation would be, this transition is triggered by one reservoir, this transition is triggered by another reservoir. Okay? And so I'm going to label these different transitions by edges. Okay? So an edge defines a transition between two nodes. And I may have more than one edge giving rise to that transition. As a result of that, I will introduce this incidence matrix, which will allow me to sum. I first write the objects and then I define them. So J along the edge is nothing but this object, but at the edge level. And now I use, this is a little bit cumbersome, but because I go to a description where I want to sum over edges, I need to specify the origin of the edge. You see, because this is pi, or let's say pj times wij. So I will have now an edge here that does this transition that corresponds to ij. But I need to say that I start from the state, which is the origin of the edge. Okay, so origin of the edge is the node corresponding to the origin of the edge. So if I have oriented edges, I will orient them always. The origin of the edge is this state, and the target of this edge is this one. But I will often say that, so this one is the origin of the edge. This one is the target, but rather than using another symbol for target, I'm going to say that it's the origin of minus this edge. Because if it's oriented in the opposite direction, it becomes the origin of minus that edge. Okay, it's a bit cumbersome, but
What do you mean by edge?
edge is a transition,
Path. You mean path?
a path. You can think of it as a path, yes. Because there might be different physical mechanisms causing a transition. Let's give a physical picture. Imagine that I have a two-level system, and I have a certain bath at temperature T1 and a certain bath at temperature T2. This transition here might be triggered by this bath or by this bath. Of course, the dynamics for the probability doesn't care about that. So I'm only introducing this because I'm going to use it later. But because I will want to do energetics later, I want to distinguish in this net transition between, let's say, 0 and 1, which part is due to the left, or bath 1, yeah, let's call it left and right. Which one is due to the left, which one is due to the right bath. And I use for that a notation in terms of edge. I have 0, I have 1, and I have one edge that will correspond to the left bath, and another edge that corresponds to the right bath. It's too small. So I have one edge that corresponds to the left, one edge that corresponds to the right. Okay? And if I orient them like this is the origin of the edge, and this is the origins of minus the edge. Okay? It's a bit cumbersome, but it's needed. Yes, so the flux now is given by this. Okay, it's the same as this, you see? It's this object here, but written now by specifying the edge. So this sum is over I and j. Now I will sum it over all possible edges. So while I had a net flux between I and j, now I split this flux into the flux due to this edge and the flux due to this edge. And the incidence matrix is the delta I origin of minus the edge. So this is the final state minus the incidence, the delta of the initial one. And this object has the property that it is antisymmetric, like this. So it means that this object, it's an incidence matrix in the sense that it's going to give me a 1 whenever an edge enters a state I, and it's going to give me a -1 whenever the edge exits state I. Okay? So if I have a graph like this, every edge entering will contribute as a plus, and every edge exiting as a minus. And so I can basically rewrite my master equation, which I originally wrote like this, by now specifying which edge is taken during this transition. You see, this was a transition from J to I. The flux, I could have written this like this, the probability flux from J to I. And now I resolve this in terms of the probability flux along one edge and the other edge. And if I look at this example here, it would be the probability flux along this edge and the probability flux along that edge. And if I sum both, I would get the probability flux. So in this notation, Jij would be J edge equal to L plus J E equal to right. Okay? Good. So this was pure dynamics and notation. This incidence matrix also makes connection to graph theory because people studying graph, this object plays an important role. And let's now move to thermodynamics, but I put, I will call this, no, first I should introduce steady state. Okay, let me first write here. So entropy balances, entropy balance. And at the moment, don't take this too seriously as entropy in a physical sense. It's still mathematics. We do math, and then we will connect to physics. Before that, I wanted to introduce the steady state. So you see if I write here? No. Okay. So what I'm going to do, maybe I'm going to write this here. What is the definition of a steady state? It's when the derivative of the probability stops changing in time. So it's when the sum over the edges, oops, I forgot the incidence matrix. Okay? So I sum all the fluxes entering, I remove my drawing here. Some edges entering, some edges exiting. I sum all of them, and the probability on the edge doesn't change. So, and this I denote SS, because now in this SS, in GSS, I replaced P by PSS. Okay? The steady state probability distribution. So this and this now is the probability such that the derivative of the probability on every node is equal to 0. Equilibrium will be a special kind of steady state where each edge is 0. That's a stronger condition, okay? Here I'm saying that the sum of the fluxes into an edge is 0. Here I'm saying that every flux is 0. Every probability flux is 0. Good. These are definitions at the moment. So now entropy balance. I will look at an obvious candidate for an entropy, but for now, let's take it as a pure mathematical object, is the Shannon entropy. And with a KB, But I will not write the KB as we do usually in statistical physics. Otherwise, I will forget it everywhere. So this is minus sum over I pi log pi. And there's a KB here, but I take it equal to 1. Okay, just so that he has the dimension of an entropy. So it means that the KB will, every entropic quantity will be multiplied by KB. It's not very hard to keep track of it. It's just that if on the blackboard, it's easier to put it to 1. Okay, so that's the Shannon entropy. You all seen the Shannon entropy, right? I think this is. And a balance of entropy requires us to look at the time derivative of the Shannon entropy, given that the probability for the evolution for the probability is given by the master equation. Okay, let's start. So first, sum over I derivative of pi log pi plus or minus sum over I pi derivative of log pi. Derivative of log pi is derivative of pi over pi. So the pi goes away. And I sum all the changes of probability. So this is 0. Because probability is conserved by the dynamics. Right? I'm summing over I, the derivative of pi. This is what gave rise to this. So that term we don't need to care about. This term, let's replace now the derivative by the master equation. I get this. Okay? And now let me do a trick that is, we play that trick quite often. I will add this. Why can I do this? Because log of a ratio is log pi minus log pj. So, and if I act with this on minus log pj, this log only depends on j. So the sum over I over I acts here. And because of this, it is 0. So when I added this, I didn't do anything. Okay? This guy here I added, doesn't change anything. I added 0. Why did I put this to 0? Because the derivative of the log is the derivative of p divided by pi. So this pi goes away with this one. And I'm summing over I the derivative of pi. And probability is conserved. So this translates into this thing. So if I replace dpi by this, I again sum over I. Because of this, I get 0. Good. Now just, again, notation to prepare for later. I will rewrite this in terms of edges. So let's see if you will be convinced by this. So why did I do that? Because you see that if I switch the indices, this is minus the log pi over pj, right? So imagine that I write 1/2 of this plus 1/2 of this. But on one of the 1/2, I switch I becomes j, j becomes I. I can, so I will have a term with log pj over pi, but this with a minus sign, I can reconvert into I over j with a minus. Okay? I can do it if you want explicitly. But as a result, it gives me this minus here. Right? Do you want me to do it, or it's fine? I'm getting the Indian, which I don't know if it's a yes or a no. Okay, I think it's you can work it out. It's really right, one half of this plus one half of this, and on one of the one half you switch the indices and you convince yourself that it's minus this. So this is only a trick. But now this is the net flux between I and J, and I can rewrite this as why did I think I forgot a minus here. PI or PJ? Yes. GE, the JI, sorry. I is the origin of minus E. Sorry, this is P. And J is the origin of E. That's why I switch off the minus. Okay. And this is I fear that you don't see anything, right? What do you see? Sorry?
Yeah, can you hear me? Yeah, so what are these DIE, E for edge, I guess?
DIE.
At the bottom, you defined just below the flux?
This?
Yeah.
This is defined here. It's the incidence matrix.
But why did it not appear in that equation that you wrote down?
Because here I have a double sum. So this is the net flux between I and J. Okay, so I'm summing over it. I have the pairs. This is why the 1/2 drops, actually. I should have mentioned this. But I'm summing over all pairs twice. So in both directions, this is why I can remove the 1/2. And this is the net flux through that. But this net flux through that I can write as the sum of every edge that goes between I and J. It's the same thing as here, right? The net can be decomposed into edges, contributions. And this is exactly what I did here. Here I'm summing really over edges because pairs of IJs are edges. And so I can replace this by the flux along the edge and summing over all edges.
By the way, how many edges are possible between the I and J? Is it only 2, right?
This will depend on the physical problem. So it can be 1, 2, 100. Yes. The third last step here. I simply replace this by the master equation. Right? So I took this.
Could you please explain what was your logic behind that PI divided by PJ? You incorporate PJ extract at the numerator?
The 1/2? This one. You agree that this, let me do it like this. This is log pi minus log pj, Okay? So originally I had the PJ one. Now I added this guy. Let's act with this guy on this guy. This guy depends only on J. So the sum over I can act on W. And this is 0. Okay. So this is the derivative of the Shannon. Now let's split it in two terms. And what I do is just add a rate and a rate. And since I add it, I need to remove it. So this is going to be sum over all edges of the log of W E P origin of E divided by okay, so I added this, so now I need to remove it. Okay? I added and removed stuff. And now I define this as entropy production. Again, at the moment, don't think of it too much as a thermodynamic object. But it has the following property. It is always positive, non-negative. Why? Because this flux, remember, is the difference between this and this, okay? And the log is precisely the ratio between this and this. So if this guy is positive, this ratio is greater than 1. So this guy is also positive, and it is positive. If this guy is negative, the ratio is smaller than 1, the log becomes negative. Negative times negative, it's positive. So it's always positive. When is it 0? At equilibrium. When all fluxes are identically 0. So this measures distance from equilibrium, if you want. It's another way to say it. It measures the time asymmetry in the probability fluxes, because these are net fluxes between forward and backward objects. So whenever there's a disproportion between going into one direction versus going in the opposite direction along an edge, it contributes to that quantity. Okay, so it's a measure of the flux asymmetry between forward and backward processes. Good. We will make extensive use of that later when I will introduce physics, because physics really will be crucially related to this log thing. Of course, you can find other positive measure for stochastic processes. The key point is that you will see how everything comes together. This will be related to the entropy in the produced in the reservoirs, and therefore, for everything to go together, these objects being up to a term that I will show, related to the entropy of the system, this having to be always positive and 0 at equilibrium, this having to be the entropy. At the end, you don't have a choice. But at this moment, it's fair because I'm doing math at the end. I'm not, I haven't argued anything about physics. We're playing with a stochastic process. My decomposition of transitions between two states into edges is completely arbitrary. So you also see that, in a sense, my definition of entropy production and of equilibrium is arbitrary because I define those edges. Everything is currently depending on the notion of edge, right? The dynamics does not care about edges. It only cares about net transitions between nodes. So this edge decomposition is kind of artificial for the moment. Keep that in mind. Okay. Now I introduce a different decomposition, which is called adiabatic, non-adiabatic decomposition. It is straightforwardly related to the housekeeping
yeah, so
excess.
why do we have this incidence matrix, D matrix there? I'm sort of stuck there. I mean, because we already have the flux which is going backward also. So why do we need incidence matrix?
I need here the incidence matrix because I need to specify, I'm looking at the probability on I. So I need to specify that I only care about those fluxes along edges that enter or exit from I. This is why you see the difference here. If you go back to the IJ notation, I have only one sum here. I am specifying I, while there I have a double sum over I and J. So I need the incidence matrix to specify that I care about those fluxes that enter and exit state I. Okay. Other decomposition, well, I take entropy production. You have the definition here. Okay, so this is by definition this object. And I do another trick, which is I have a problem that my sums and my sigma, they look alike. I never know how to solve that problem. It's kind of obvious from the context, but so this is a sum. What do I do now? I replace the P by the stationary, the steady state P. Since I do that, I, of course, need to remove it from the other side. And I had the original one. No. This is minus, so do I want the minus? No, let me do it with the plus. So I need to remove it, but I want the plus here, so I need to invert, yes. So this is going to be PSS minus E over PSS E, and I put back those ones that were already there. Okay. So you see this, the log of this is minus the log of this. So this goes away with this. And then this with this is this. Okay, so this part here, I added, but I removed it. And this part was there. Okay? Okay, we remove this, keep this property in mind. Now I will show you that both of these quantities, so this one I will define as the adiabatic entropy production, this one as the non-adiabatic one, and we will prove now that both are non-negative. Okay? So let's start with the adiabatic. I will use again the trick that this is the difference between forward and backward flux, and this is antisymmetric if E goes to minus E. So I can, it's very similar to what we did before. I can rewrite this as twice now. Why do I put a minus here? Ah, just because I will need it later. Let me do it step by step. Okay, so and I have a factor 2 here because, again, this is W, I just removed it, but it's W so if I send E to minus E, this becomes minus, right? And same thing for the log, it becomes minus, so I can write this like this.
How that first term is corresponds to adiabatic quantitative setting?
I will discuss their property now, but let me first work out the proof of positivity. The meaning of those quantity, I need to rewrite them in different ways to discuss it. At least not that one, but the next one. Now I use a property that I always remember like this. Log of x is always greater than x minus 1. Which means that minus log x is always log x? No, it's the opposite. I just have it. X minus 1 is always greater or equal than log x, and therefore minus log x is always greater or equal than 1 minus x. Now I use this here, so I have twice sum over I wi. 1, the first term is 1, and then minus twice the sum over, and this is minus x. Ah, no, I forgot to do the inversion I mentioned just allow me to, I just do this, same thing, sum over E. I put a minus, and I revert the log. Okay, so that, because I wanted minus log x, this is why I wrote it here. So minus log x I replace by the 1, which is with the minus. And the second term is going to be now a plus. No, what am I doing? This is a plus, and this is a minus. And now I have W minus E, P origin of minus E steady state, divided by W E, P origin. Voila. And I have this going away with this. This guy is nothing but the sum over ij, wij, pj. And because I sum over I, this is going to be 0. Okay? From here to here?
Second line, is that equal to or greater than?
Ah, la, la, la. Yes, sorry. Yeah, because I use this inequality here. So I used it for this. This is minus. If you want, I can put the minus here. I use the inequality inside this. And from here, I go to the third line. Yeah, sorry, this I should have put in the middle. So this is 0, and the next term I can also rewrite as no, wait, I should be careful here. This is the steady state one. So I can cancel the W's, but not the P's. Okay, so this goes away with this. And now I want to rewrite this for convenience again in terms of a sum over I and j, wij, pj. I need to be careful with the order now. So, because if I write okay, let's say that E is ij, so minus E is ji. Then this is minus E, so this will be ji. The target is I. Steady state times P. This is J, and this one is J. Yes. Okay? So it's a bit confusing because of the minus I. So I choose my edge as ij, so minus the edge is ji. And of course, it's a sum of all these forward edges that gives ij, but since we have a double sum, it's fine. When I act with this on this is by definition of the steady state. You see sum over I, W, Ji, P, I, steady state, this only depends on J, this term will also be 0. Okay, what can we say about the meaning of that quantity? If the steady state is an equilibrium steady state, what did we say? We said that the net fluxes, every net flux is 0 at equilibrium. And the net flux is this minus this. So it means that if we are at equilibrium, this is 1. And so by construction, this log is always 0. So if the steady state is an equilibrium one, then this quantity is 0. And this is a statement not only when I am at steady state, it's a statement about at any time, right? Because here I have the actual P. Here I have the steady state P. So this quantity is always 0 if my dynamics is such that the steady state is an equilibrium steady state. So if you want, it measures the break of detail balance, this asymmetry, in the steady state. But it is weighted by the non-equilibrium flux, because this J contains the actual P. Okay? Now, this is more of a side comment that I may use later, but because this quantity kind of appears here, I can rewrite this rate times this divided by this. This is sometimes called the dual rate, which defines a dual dynamics. So it's defined like this. Okay, so this is a definition of the dual rate. It's also this dual rate. So I can define a dynamics with this object, which is a rate. It's a rate because if I sum, it has a property that if I sum over I, W, I, J dagger, it is also equal to 0. And the dynamics with this W, this I will leave as an exercise. It's actually very simple. But you can prove that the dynamics generated by this rate, so the dual dynamics, which would be something like this, dt pi. I put a wiggle because it's a dual. This dynamics has the same steady state as the original dynamics and minus, so the steady state currents of the dual are minus the steady states of the original dynamics. So this means that the dynamics is different, but at steady state, both have the same probability distributions. And the dynamics of the dual reverts the direction of the fluxes. Okay? So this is, we can do this as an exercise, and maybe this afternoon we can do it.
So I think there you put that sigma a dot, the adiabatic dot is identically zero. In the
No, I proved that it is positive, right?
oh, positive, sorry.
You made you pointed out that I forgot the inequality, so that it is positive. Yeah. So that quantity is always greater or equal to 0, but it is 0 for a dynamics that is detail balanced. Okay, so this was for the. Now let's move to, for the adiabatic. Let's move to the non-adiabatic. I'm way too slow. I knew it. Okay, the non-adiabatic. So let's first prove that it is non-zero. So yeah, it's still here. These are all state quantities. So I can again move to the ij notation. Let's check the ij direction again and with the signs. So I put here j, bj steady state, I steady state, j steady state with the yes, without this, because this goes from j to I, so the origin is the j. Yes, it's correct.
When you go from edge rotation to ij, you should get choice just like
No, because I do two things. I go from edge to ij, but I also go from the difference between w and edge, w minus edge, to a sum over a single one. So I actually get a 1/2 and then a factor 2, which cancel with each other. So it's, again, do it as an exercise. Otherwise I will really get too slow. But it's the fact that I go from edge to ij's that give me a first factor 2. But then that factor 2 gets removed by the fact that I go from j, which is a difference, to a single one, using again this trick of splitting, putting together the two sums. Here? Yes. Thank you. Yeah. Good. Now I put the minus because I will use again this inequality here. So the first term is the 1. So let me put the minus here. So this term is again 0 because sum over I, W, I, J. And the second term is x, so this one is going to be minus sum over ij, wij, pj, pj. Okay, just a second, I finished this. What did I do? Yes, you're correct. It's this one. No, good, because otherwise I would have been stuck here. Yes. So this goes with this. No, I still. Yes. Thank you. J. No, I think this is correct, no? This is correct, I think. J. J, J, I. This is correct, I think. Big. And then if I invert, I get the J, the I, and then when I get here, I get the J. This is the I, and the ISS. Yes, this is what I need, because if I sum over J, by definition of the steady state, sum over J, Wij, Pj, this only depends on I, it is 0. And so this is also 0. Okay, so we proved that these two quantities are 0. To understand the meaning of the non-adiabatic one, it is actually better to rewrite it differently. And I'm going to use now the fact that, again, splitting the log into the J part and the I part, the J part, I can drop it because I can sum over I, and then it's equal to 0. So this I can rewrite as the sum over Ij, Wij, Pj. I kept it there because it was convenient for the proof, but it's actually equal to this. Okay? The argument is splitting the log in a difference, and then noticing that this part of J only depends on J, so if I sum over I, it is equal to 0. This means that I can rewrite this quantity, so I invert the order of that and I put a minus, sum over I, derivative of Pi log Pi over Pi steady state. And this I can rewrite as minus the derivative of sum over I Pi log Pi over Pi equilibrium minus the sum over I Pi derivative. This goes with a plus. I will tell you why. This is steady state. Okay, so what did I do here? So from here to here, I only use the master equation. This was an I. So I change the order so I get the -1. And then I have this sum over I of this, which is the time derivative of P. This is only using the master equation. And now this was derivative of P. I rewrite it as the derivative of this full object, which is a relative entropy. I will say in a second. But then I need to remove the part with the log, the derivative of this log. And since I put it back up, I get the minus sign. And so this part removes the term that, because I took the full derivative here, I remove it here to get this. Okay? Now this object here is a so-called relative entropy between the steady state distribution. The relative entropy is always greater or equal than 0. It is used as a metric to measure how different the two distributions are from each other. It's again an information theoretic quantity, so it's really defined like this. And it is by construction non-negative. And it is only equal to 0 when P becomes equal to P steady state. Okay? So now we have something that allows us to, the proof of the positivity is again a trivial application of this. You can do it yourself. It's a one line. So what can we say about this? You see that here I have the time derivative of the steady state distribution. I should have emphasized something and I forgot. Is that my rates, everything I did from the beginning holds for time-dependent rates. I never had to assume that my rates were time-independent. My definition of steady state becomes, of course, time-dependent if my rates are time-dependent. You should think of it as an instantaneous steady state. Okay? You're summing all the incoming flux instantaneously. It's equal to P stationary. So the stationary distribution becomes an object. If of course, you drive your rate fast, your distribution is not going to be in the steady state. But the steady state is still a well-defined object. It's the right null vector of the rate matrix. Okay? It's defined simply like that. So you have the matrix W, and let's write it like I did it. So sum over E, D, Ej, J, steady state is equal to 0. So even if my rates here are time dependent, this object is time dependent but well defined. Okay? It's an instantaneous steady state. But if I don't drive, if my dynamics it's called autonomous. When I drive, it's called non-autonomous. So for an autonomous dynamics, this term is going to be 0. Okay? So autonomous dynamics so think of it as no driving of the rates. Sigma non-adiabatic is minus the derivative of this relative entropy between P. Sorry? It's too small. This, okay. This is autonomous dynamics. No driving. Okay, so I rewrite this. Minus time derivative of the relative entropy of P and P steady state. And we proved that, sorry, this is the non-adiabatic. And we proved that the non-adiabatic is also non-negative, okay? So this shows that these relative entropy, which is also a convex function, goes for autonomous dynamics, always goes down until it becomes 0 at steady state. Okay, so this shows you that this relative entropy here is actually a Lyapunov function of the dynamics. Your dynamics is going to minimize this object until P reaches the steady state. Okay, so it can be used as a way to prove that P is going to go to P steady state for an autonomous dynamics. If I drive, it's different because I have this additional term that prevents my system from reaching these steady state. Okay, and now this somehow brings us to the reason for the terminology is that this non-adiabatic entropy production has to do with time-dependent effects away from the steady state. This quantity is going to be only 0 at steady state. Okay? So it captures the two different mechanisms for dissipating while not being at steady state. One is simply that I started from a non-equilibrium P, and so while my non-equilibrium P relaxes to P, I will have some dissipation. Or even this additional mechanism, which would be if I drive my system and I prevent it to even reach steady state. So it has these two contributions to it. But both have to do with phenomena that are not in the steady state. The adiabatic one is a measure of, in the steady state, how much I dissipate because my steady state breaks detail balance. Okay? So this is the reason for this terminology.
So by drive, drive has to be time dependent?
Yeah, it's true that I use driving typically. It's yeah. So I will specify it. It's a good point. No time-dependent driving. Yeah, the mathematical, I think autonomous is mathematically correct, but no time-dependent. Yeah, I know, and people get confused. It's because I have non-conservative forces also that can also drive the system. So it's a good point, and I think it's good to specify that it's no time-dependent driving. Good. So in the last 5 minutes, let me make a comment on coarse graining. Maybe there are things I may not want to erase. No, okay. So I am going way too slow, and so I have a question, which is it better to continue at this pace? Do you prefer if I continue at this pace and we see less, or I speed up a little bit by skipping some steps and we see more? So this pace I keep. Okay. we might not get to macroscopic. Okay, the last comment I want to do, I think it's a good point to stop because I didn't put the physics in, and the physics I will put it in tomorrow. So it's the following comment. We had this definition of entropy production in terms of edges. So let me define a wiggle. It's not the same wiggle as the dual. Okay, it's another wiggle. Entropy production, which is only expressed in term, now I put the 1/2, in term of the net rates between states. And this I can rewrite as ij, w, ij, pj. I will use this. There's a thing called the log sum inequality that allows me to prove, so remember that we had the original entropy production that was written in terms of edges as So the difference I emphasize is that in this case, we sum over all the edges that connect, let's say there are 3 here, E prime, E prime prime, that connect I and J, while here we lumped everything into a net rate I and J, okay? So by summing all the WE corresponding to the same pair of ij, I can actually prove that this is a lower bound to this one. This is the log sum inequality. Because it says that if I have something like this, it is always, and it's again a property of the logs, smaller or equal than so you see here the sum is on everything, while here I entered the sum, it's the sum of this and the sum of these guys. And so because these rates here, these are the sums of all of these rates, the log sum inequality applies. Okay? And so the entropy production in terms of edges, the one I presented as the entropy production, versus this one, which is coarse-grained because it doesn't resolve the fluxes, the different fluxes connecting to the different edges. So this one is smaller than this one. Coarse graining underestimates this entropy production. It's a mathematical statement. For the moment, it adds to the puzzle. Why did I add these edges? Right? Because I defined the entropy production in terms of those edges, but again, the dynamics doesn't care about the edges, about the fluxes along the edges. It only cares about the net fluxes. But I decided to split fluxes in terms of edges. And this is because the physical processes will be associated to edges. Every edge will be connected to what happens to the reservoir. And this is why this will end up being the physical entropy production. that if you have only one reservoir is equivalent to this one, because then you have only one edge connecting two nodes, but in general is not. Okay, so this was my comment on coarse graining. Voila, so this, until now, math. Next time, we come with the physics. Can you speak louder?
When the edges are moved, you say that entropy.
Yeah, entropy production goes up because I add more routes for dissipation. You remember that the meaning of this entropy production is to measure the asymmetry between fluxes along every edge. So here I have many edges, and I'm summing these asymmetry along each of them, while this one only cares about the asymmetry in the net probability.
But so for a fixed net probability, you can have, you can add mathematically infinitely many
Yeah.
edges, and thereby you can increase the production to the
Yeah. So for the moment, it looks like it's almost a way to say, but why am I adding those edges? It looks arbitrary.
Because if you know, there is there a bound, like upper bound, like
No, it's true. I could, in principle, add as many of them, and I could, as you say, I could make this arbitrarily large while this remains finite. But my point will be, I anticipate, these edges have to do with flux exchange with the reservoirs. And they are really the cause of the physical dissipation. And this is why there's a lot of people taking definitions from stochastic thermodynamics and applying it a bit carelessly, where people think that this object here is always the entropy production. No. This object is only the entropy production, the physical one, in specific contexts where there's only one edge, which you will see is one reservoir, causing the transitions. If you have multiple mechanisms, it is not. And this is very important also for all this question of estimating entropy production. Because if you're only monitoring transitions between states, and you don't monitor other degrees of freedom, you're going to miss a significant part of the entropy production. So that's why I wanted to emphasize this difference between these two different entropy production. But I think it's going to become clearer once we add the physics explicitly to the edges and to showing that this log ratio of the forward and backward rate are connected to the physical quantities, energy, particle exchange, and ultimately entropy change in the reservoirs. So this was a mathematical prelude, but we will use a lot of the property that we described today.
Will you be there in the
Yeah, I think I will be there. I don't have specific, I mean, I gave a few suggestions of things to try. You can try to make those proofs, and then we
so
can
in the
discuss.
tutorial, we can, like, you can ask questions again if you have things to clarify. Okay, so no questions, then we break for lunch.
transition matrix, which is like two sides are not connected directly, but then if you take a m square, just the transition, not like this, like only the transitions are equal. So then if